Okay, in this video we're going to talk a little bit about the types of data in a computer. As we know, everything is stored as binary in a computer, right? We know that because the computer is really a circuit, and circuits communicate with electrical charges, electrical signals, and binary data can be stored using voltages. So a wire with a voltage of 0 could be representing a 0, and a wire with a positive voltage of some kind could represent a 1. And so that if we have one wire, that can be 1 bit of data, either a 0 or a 1. If we have two wires, we have 2 bits of data, either a 0, 0, 0, 1, 1, 0, or 1, 1, right? And so however many wires we have, that's how many bits of data we have. So computers have been engineered to have a tremendous number of wires, if you want to think about them as wires. And the storage capacity is extremely large these days, okay? But fundamentally, all the computer types of data are stored as ones and zeros. So we need to think about the format. How are these ones and zeros, how do they store all the different types of data? Okay, so when we think about programming, there are some primitive data types that we're used to, right? So integers, right? Positive numbers, for example, those are easy to think about. Positive integers from 0, 1, 2, 3 on up to some limit. Well, how can we store those? That's pretty obvious, right? We would just start with some predetermined size of number of bits to store this in, right? And if you have some predetermined size of data, then there's only so many values you can store. So, for example, if we had 4 bits of data, how many different items could we store? How many different values can you store in 4 bits of data? Well, it's base 2, so it's 2 to the power of however many bits you have. So this is 2 to the 4th power, which is 16. So here we see binary 0, 0, 0 translates to decimal 0 on down. And as we get to number 10 here in decimal, we've run out of our digits. We only have 9 digits, 0 through 9. Once we run out of those digits, we add a 1 to the left and add a 0 placeholder in the 1 space. Hexadecimal, however, has 16 digits, right? And so for the number 10, we use the letter A, B is 11, C is 12, right? But everything in this row corresponds to the same value. It's just different ways of representing it. Okay, so in terms of storing a positive integer, if I have, say, 4 bits of data, it's pretty easy. I can store up to 15 or 16 values if I include 0, and I just start with 0, 1, 2, 3, 4, and on down the line. Now, what happens if I want to include something like negative values? Well, I have to rethink this a little bit, right? So going back to our picture here, if I have 4 bits of data, well, in 4 bits of data, I can only store 16 values. So if I'm limiting myself to 4 bits of data, and I want to allow for negative values, right, I probably want to have 0 somewhere in the middle, right, and then 7 or 8 negative values, and then 7 or 8 positive values, right, something like that. So what we could do is we could partition off these bits. We could say, okay, for the numeric value, I'm going to use these 3 bits, right? And then for the positive or negative sign, I'm going to use this first bit. Okay, now this is just theoretical. We're just toying around with ways that you could potentially do this, right? This isn't an official standard or anything. But it makes sense that you could store the data this way, right? It would be possible. So we have 3 bits that represent the quantity, and then we'll say this very first bit, if it's a 0, then that's a positive number, and if it's a 1, that's going to be a negative number. So here this would be 0, and then 0 is positive, so this is positive 1, positive 2, positive 3, 4, 5, 6, and 7. So these are all positive numbers. Now here, this gets a little complicated because we have a 1, but also that means it's negative, but then we have zeros, right? So the one issue with this particular system would be there would be 2 ways to represent the number 0. You would have a positive 0 and a -0. But other than that, it's pretty straightforward. Here is 0, 0, 1, so we have a 1 leading, so that would be a -1. We have a 1 leading, so this would be -2, -3, -4, right? All the way down. So 0, 1, 2, 3, 4, 5, 6, 7. So with this system, we have the numbers -7 to +7, which is 15 numbers, and we have 2 zeros, right? So that would give us our 16th because we have a second 0. All right, so that's one way we could potentially store negative values. But notice how the range was cut in half because we had to remove one of the bits that we would normally use for the quantity, right? We had to remove that, and we partitioned that off to use that as an indicator of whether it's positive or negative. So that only left us with 3 bits. So we have fewer bits to represent the quantity. Okay, but this idea of partitioning off the block of data where different bits mean different things in the context of what type of data is being stored is going to be important. All right. So let's look back at some of our other types of data. All right. So we got positive integers. We've got negative values. What about floating point decimals? Okay. Well, floating point decimals might be the same type of thing. Let's say instead of 4 bits, we're using 8 bits of information. I'm going to put a little space in between just so it's a little bit easier to read. All right, so we might do something similar. We might say, okay, well, for a decimal number, we're going to use the 4 bits we used before for a positive or negative value, right? And then we're going to use 4 bits to determine maybe a power and where that decimal point should go, right? So if this was, and we could have positive, this is another positive or negative number, right? So this would be the quantity, and then this would be multiplied times 10 raised to this power, right? So if we had negative 1, right? And we had the value, this is binary value 2. So this would be 2 times 10 to the negative first power, right? So this would be 0.2. Right? If we wanted to raise it to the 10th power, right, we would do something like that. Whoops. There we go. Okay, so this would be 2, the number 2, times 10 to the first power. All right, so that would be 2 times 10 to the first power, which would be 20. Right? And so then we could do the 0th power, right? So that's 2 times 10 to the 0th power, etc. So this second chunk is basically a way of determining where the decimal point goes in our number. All right? So we would still have, this at the beginning would determine the positive or negative value of our quantity, right? So if it was a 1, this would be -2 times 10 to the 0 power, something like that. And again, this is just one way we could represent this data, right? It's just one example. There are lots of different ways, and we're only using 1 byte of data here, right? So modern computers have much more bandwidth to work with, right? 64 bits usually. So you can do a lot of different things with 64 bits of data, all right? So floating point decimals, we've got kind of at least one system that can kind of work. What about string data? All right. Well, actually, let's label this down here. This is quantity, and then this might be power of 10. All right. So string data. How do we deal with string data? Well, we've seen before the ASCII table, and we can open up ASCIItable.com, and you get this nice little chart of all the binary representations of every symbol that we use for characters, right? Now these are English symbols, right? So this is everything you see on your keyboard. So every single one of these characters, a lot of these we don't know much about, right? These are control characters. They're not used very often. We don't see them as users very often. We know about the tab character, maybe. You might see the line feed or the new line and a couple others, but that's about it. The characters that we're used to here are starting in this column here, right? The space bar, different symbol characters, brackets, that sort of thing, and then the numeric values 0, 1, 2, 3, all the way down to 9. Now notice, these values are represented by a number 48, right? So the 0 symbol, the 0 character, is actually stored in the computer as the number 48 in binary. Okay, the number 1 is not stored as the number 1 in binary, it's stored as the number 49. Okay, so the way this works, we're going from the decimal value 0 all the way up to 127, right? So 0 to 127, that's 128 different values, which is 7 bits. 7 bits of information, right? And so usually a single character is represented by a byte, which is 8 bits. So there's 1 extra bit when we're representing character data. Okay, and this is just the ASCII code. There's lots of different character formatting codes. Okay, so ASCII was one of the first ones invented or used prominently, and it's just an agreed upon mapping. If we have a binary number and the type of data is string data, ASCII string data, then this number represents this character. So a 52 represents the symbol 3. Right? And so you can think of these symbols really as just little tiny pictures that are printed to the screen. Right? This is just a picture as far as the computer's concerned. Right? The actual number being stored in memory or on the hard drive would be this number, 51, except in binary form. All right? So if we had a byte of information, right, and we had the letter A, right, that would be the number 97, right? If we look at our ASCII chart, right, the lowercase letter A is 97, right? It's also the hexadecimal value is 61. All right, what would the binary value be? All right, well, we can use Python to help us out with that. I've got this file called number systems, and I'm just going to type a little Python code in here. We can convert numbers with Python into different number systems. So to convert something to binary, I can use the bin function, and I can convert 97. So that's anything I type in as an integer literal in Python is assumed to be decimal. Okay, so this is an integer literal in decimal format, and I want to print out that value. All right, so I can run my little program here, Python 3, number systems. Okay, now see how it prints out this binary number. It starts out with this prefix OB, okay, the 0 and then the B. The B stands for binary. So what this is saying is this string is supposed to represent a binary value, but what's to the right of the 0B is the actual binary value associated with the number 97. Okay, so let's see that we have 1100001. Okay, so that's 7 bits. So if we go back to our types of data, right, it was 7 bits, not 8. Right, and it was 1100001. Is that right? 1100001. Yeah. Okay. So this is equivalent to the character A. Right? Now in Python, I can represent the same value as a literal, but I have to use that 0B prefix. that's telling Python, okay, I'm about to enter in a number, but it's in binary format. So I can say 1100001. And if I print this out, see the 0b means this is a number, but it's in binary form. Python prints it out as the decimal version. Okay, so whenever you have a number and you don't specify how you want it to be printed out, it's always going to be printed out in decimal format unless you specify some other way, like using the bin function. We can also use the hexadecimal function. Print hex, and I want the hex value of the decimal number 97. Or I could have the hex value of the binary number, which also is 97. OX is the prefix for hexadecimal. Okay, so you'll see this a lot. A lot of times when you reference memory locations or addresses on hardware devices, you'll see something like this, OX and a bunch of hexadecimal digits. That's meant to represent a very large binary number, right? And instead of writing it out in binary, it uses hexadecimal because that takes up way less space. Okay, we see the same number here is 7 bits, right? 7 digits, whereas in hexadecimal it's only 2, right? So that saves quite a bit of space. So for every 4 bits of binary, you can just use one bit of hexadecimal. So it's literally 4 times binary is 4 times larger when you write it out than hexadecimal. Okay, so, and it's also a little bit harder to keep track of all the ones and zeros. With hexadecimal, you at least have a chance of seeing the different digits, and it's a little bit easier to read. All right, so remember the 0b prefix allows us to specify integer data, but in binary form. So this is an integer literal, but it starts with the 0b. But I could also do the same thing with hexadecimal. So I could print out 0x, and then this is going to be an integer literal, but I can type out 61. And as we saw, OX61 is the same as decimal 95, or 97. Okay, so we got 2 97s there. All right, so when we're looking at types of data, you know, we see this concept that it depends on how you format this data, right? This is just one byte of data any way you look at it, but what type of data it is determines what it means conceptually, right? And how it's going to be used when it's sent to the processor, right? The processor can add two positive integers or you know, 2 integers together mathematically, right? But it doesn't make sense to add 2 characters together, right? You theoretically could and you'd get a result, but it's not necessarily meaningful if the data was representing a character, right? If it's representing a character, then adding the 2 numbers together doesn't really do anything meaningful to you, right? So one last type of kind of primitive data that we need to talk about is Boolean data, right? And Boolean data is true or false, right? Boolean is just a 0 or a 1. Okay, so if I had, you know, 8 bits, well, that might be false. Let's say this, you know, equals false, and then a 1 might equal true. Right? That's wasting, you know, all of these bits basically. Well, if your program has more than one Boolean value or one Boolean variable, right? This 1 bit will handle one Boolean variable, but then the next bit could handle another Boolean variable. Okay, so there are ways you could set this up where 1 byte of data could represent various Boolean flags, right? So this could be this would be false, false, true, false, and then true, 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 false. But this is at a very, very low level, right? Programming languages like Python or something like that will do all this for you. You wouldn't have to manually set this up, right? But the idea being is we can pack in multiple variables into 1 byte of data if we need to, right? So conserving space is often an issue. Not so much now as it used to be. It used to be very, very expensive to store data on a computer. The size, the amount of storage or memory that you had was very, very minimal. And so there have been extraordinary techniques developed to reduce the amount of space a program uses or the amount of space it takes up to store different types of data. Okay, so these are all just theoretical examples of how you could store data. The only one that's actually relevant, actually a real protocol here is the ASCII code, right? We saw that at the ASCII table, and then also true and false, like you can store data like this, right? The other two, usually it's a little bit more complicated as far as the way you store integers and Boolean values, but you can see conceptually how you can do it. All right, so real quick, let's jump into a theoretical memory example. All right, so we have memory, computer memory, which is basically where we store values. When we're running a computer program, any variable data that we have stored is going to be stored somewhere in memory. And the way memory is set up is there are addresses, and that way the computer can access data at a particular location. If there were no addresses, you wouldn't be able to access the data. It has to know where to find this data. All right, so we have addresses here, and in this example, we have basically 1 byte of addressing space. Okay, so this is just the hexadecimal version, and this is the binary version, right? But the values are the same. You wouldn't really have both hex and binary, right? But the address is here, and it starts at 0, and it goes 1, 2, 3, 4, all the way down until you run out of addressing space. You would run out of addressing space at 2 to the 8th power, right? So you could use Python to see what that is. 2 to the 8th power, right? 256 storage spaces, 256 storage locations, memory addresses, right? So for each one of these, we're going to be able to store 1 byte of data. Okay, so let's say Python wants to store a number, right? So what it might do is it might say, okay, memory location 0 is free, and I want to store a number there. All right, so this first byte might be the type of data, and so all of the different values we can store in this byte would be the type of data that we're going to store next. Okay, so maybe something that's very common is an integer, so that might be the value 1. So the type of this data is value 1, right, meaning an integer. So that means the next byte will say, since our integer schema up here was the first bit is either positive or negative, right? So we might have a negative, and then this might be negative 3. Okay, so Python has a pointer here, right? This is Python variable. Now this is a very loose example. This is not exactly by any means what happens, but this is supposed to help you understand kind of what's going on under the covers in a computer, right, when it's storing value. So Python variable is actually, I guess this should point the other way, right? It's pointing at this memory address, right? It's storing this memory address, and so when I access the Python variable, it says, okay, well, this is type integer. With type integer, that means the very next memory location is going to be the actual integer data. And then that's the end of my value, okay? All right, so that might be, kind of the end there, just with respect to Python. But these values could be reused at any time by other parts of the program if they get freed up. But now this memory is in use, okay? So it can't be used by other programs, right? It's in use, it's allocated, right? And again, this is a very loose example. All right, so we might have another Python variable. So this might be, this is variable integer x holds 3. Or this is just the integer literal 3. right? And then Python here might reference a string. Okay, string data might also be very common. So the type here might be the number 2. So this would be the type. And then with string data, since it's a series of characters, the very next block will be how many characters are in the string, right? Because we know strings can have quite a few characters. Well, in this case, we'd have a limited number of characters because we have 1 byte of data, so that means we could have strings up to length 256, right? So let's say the length of our data here might be 3. Okay, so again, the first item when Python is pointing at a memory location is what type of data is stored here. That's the first byte, and the second byte depends on what type of data we're dealing with, right? We saw if the type was integer, then the next byte is just the integer. Right? With string data, the next byte is how many characters, and then based on that value, we have 3 characters, so that means that byte, and that byte are all part of our string. Okay, and so I guess this is a literal integer, and then this would be a literal string and cat. Alright, so the type of the data, this is the number of characters, and then the letter C, A, T. Alright, well, let's look at our ASCII table, and we have C is 99, A is 97, and then T is 116. Alright, so let's pop over here, and we can print out cat and print out the binary version, right? So we can get the ordinal version of the letter C, which we saw was 97 or 99. The ordinal just converts the character into the ASCII value. So we run this program. Okay, so that's 99. We saw the ASCII value of C was 99. The ordinal value of A should be 97, and the ordinal value of T, or ASCII value, should be 116. So 99, 97, 116. So that's correct. But we want the binary versions of those. So let's see this. And notice the bin function actually returns a string value, because otherwise it wouldn't be able to print out the zeros and ones, right? Because if it just returned a binary literal, Python automatically converts those to decimal whenever it sees them, right? So the bin function actually returns a string. Okay, so these are the values that would be stored. We have 110, 0011, so we'll copy that, and we go back to our types of data, and we have this is getting stored here. Right, so that's the letter C, and then we go back and we can copy this. And that's the letter A, and we can go back and copy this one. And that is the letter T. Okay, so you can see how when memory is allocated, any data stored on the computer really is, it depends entirely on how it is partitioned up, how it is sectioned off. Even within these bytes themselves, so like integer data, we use that first bit, we partition it off and use the others for the numeric value, but that first bit is the positive or negative, right? But even groups of bytes, right? We do the same thing. We partition this off and we say that first byte is the type of data, and then the second byte means something else, and then the rest are a series of items, right, of that type, right? I could even have a list of other items where each one of the items stored here might reference a different memory location. So for example, if I have a list of items in Python or an array, right, each one of these items in the list, right, would be a memory location to look up, and in that memory location there would be a type of data, a string data or integer data or something like that. Okay, but this is very loosely how memory addressing works in a computer and how different types of data can be formatted. And it's really important that you at least conceptually can understand how this is possible. The actual formats used in the actual systems are much more complicated than this, but this gives you a basic idea of how things operate memory-wise, and even in physical storage, long-term storage, like solid-state disk drive or a hard disk drive. A similar scheme happens where there's an address and then a big chunk of memory. So it would be more than a byte, especially in hard disk drives or solid-state drives. You'd have a block of data, right, which might be 512 kilobytes or something like that. All right, but the idea is still very similar. All right, so this has been a general explanation of types of data and how data is stored in computer memory and on hard disks.